We've already talked about this idea of vector notation when we've looked at the translations. The idea that a vector, something like, say, this, or, say, this, could be used to give directions on a coordinate grid. Coordinates, remember, single points in space. Vectors, directions, movement between one point and another. Number on the top, number left and right. Positive number for right, negative number moving left. Number on the bottom, up and down. Positive for moving up, negative for moving down. So this first one, for example, would be 3 right and 4 down. Move 3 to the right and then move 4 down. And the other one would be move 10 to the left and then move 6 up. So vectors giving a direction. Starting point and finishing point are not listed. Notice that's important, but the direction is. Now there's more we can do with vectors than just describe simple directions, because it turns out that we can consider more than one vector at a time. Consider 2 different vectors, often called column vectors because they are numbers in a single column. Well, let's think about that particular vector, and let's think about this particular vector. Now they both describe different directions. The first one, 4 to the right and 5 up. The second one, 2 to the left and 9 up. Imagine that we wanted to use those repeatedly for something, use them more than once. Well, why don't we use a shorthand way of describing them? Why don't we call this first one perhaps direction A, and this second one direction B? Nothing wrong with doing that. We could do. We're just going to give them a label, so that if we say to someone, oh, move that according to direction A, then they'd know what to do. Move that according to direction B, then they'd know what to do. As long as we define this kind of shorthand, then we're okay. But now that we've done this, now that we've defined those 2 particular directions, we could always think about those directions happening more than once. We could think, for example, about having 2 lots of that direction A. Well, this 2A, if A is 4 to the right and then 5 up, 2A would just be do that direction twice. So we'd go 4 to the right and then 5 up, and then 4 to the right and then 5 up. Let's just draw that out just to make this clear. That's 4 right and then 5 up, and then 4 right and then 5 up. Well, we could think about the overall effect of that. If we've gone 4 right and then 5 up and then 4 right and then 5 up, we could write that as an overall direction, as one single vector, one overall direction. So 4 right and then 4 right again. Overall we've gone 4 and then another 4, we've gone 8 right. So our top number could be 8. And overall we went 5 up, and then later on we went 5 up again. Well, overall that is 10 up. So our top number could be 8 and our bottom number could be 10. If we're writing that 2A as a single column vector, we can just give that as 8, 10. Really though, what have we done to get there? Well, let's compare that to the original. What we've done is we've doubled the top and we've doubled the bottom, and that makes sense because we've done the top part of the direction twice and we've done the bottom part of the direction twice. So in fact what we've done is we've done 2 lots of the 4 and 2 lots of the 5, and then we've ended up with a final column vector for that. The upshot of that is that if we wanted something like 3b, that's 3 lots of the direction B, that vector that we've defined as B, just using that kind of shorthand. Well, if B is -2, 9, we're doing that 3 times. So we're doing it once, then again, then again. So we'd have 3 lots of the top number and 3 lots of the bottom number, because that's how far we would move in total if we looked at the final end point compared to the original start point. Well, that means we've gone 3 times -2 is -6 on the top, and 3 times 9 is 27 on the bottom. And it's important to remember that these are always directions, whether they are written as a letter, clearly coding for a vector, or just written in the vector form. We're just applying that direction more than once. Do the instruction and then do it again, possibly do it again, and so on. And we're summing that up as a final direction, an overall movement from beginning to end. Now we could also start to do things like looking at one direction and then the other. So we could look at something like A plus B. That is direction A and then do direction B. Well, direction A has us move 4 right and 5 up. And direction B has us move 2 left and 9 up. And we're adding those together. We're doing A and then we're doing B. So how would we deal with that? Well, let's think about this one at a time. If we move 4 right and then we move 2 left, overall, surely we've gone 4 right and then we've gone 2 back again in the other direction. So we've just gone 2 right. And 4 plus minus 2 is 2. So we just need to add the numbers. And if we've gone 5 up and then we've gone 9 up, well, surely that's 5 plus 9 is 14 up. So it turns out we can just add the bottom numbers as well. So adding vectors or multiplying vectors is just a case of doing that, exactly that we're given, the multiplication or the addition, to the top numbers and then doing it to the bottom numbers. And it is worth noting that there are some connections with algebra here. This idea that we're using shorthand notation rather than for a single number this time, we're doing something called vector algebra. We're doing algebra, we're using this shorthand letter-based code system, but to describe a direction rather than a single number. We're using it to describe a movement, a translation, a direction. And like with normal numerical algebra, sometimes we're going to have letters that stand for particular numbers that we know or that we find out. In that case we've just seen, we had the identities of A and B. We knew the directions that A and B were coding for. Sometimes though, we might not know, and we might just have to work with A and B, or whatever, as directions that we know are directions, we know are vectors, but we don't know exactly what they are. And that's where questions like this one come in. A, B, C, D is a parallelogram. The diagonals of the parallelogram intersect at O. So there we have a parallelogram, A, B, C, D, and we have this point O in the middle. There are 2 diagonals given to us, one running from A to C and one running from B to D, and they cross at some point O in the middle. And then we're told underneath further. And then there's this OA with an arrow over the top equals A, and OB with an arrow over the top equals B. Okay, couple of technical points here. This is purely notational. OA with an arrow over the top is the direction from O to A, in that direction. And OB is the direction from O to B, in that direction. If we wanted to go the other way, we could either point the arrow the other way, or we could swap the letters over and have AO with a right pointing arrow. The direction of the arrow matters, because that tells us which way we are moving. Next thing to notice, equals A and equals B. Well, look at the diagram. A and B are also listed on the diagram. They're listed with little arrowheads there, and they are given A is on the line from O to A, and B is on the line from O to B. No particular surprise there, because it's given here. In fact, A and B are vectors. And these notations are just different ways of writing a vector using that kind of code. A and B are more of an algebraic code, more of a kind of algebra that we would use. The reason they're in bold is so that you know that they are vectors. The use of bold font there just signals them as a vector. So, to make that really clear, there is a particular direction, set of instructions, some left or right, up and down, that gets you from O to A. And if you started at O and followed those directions, you'd end up at A. That set of instructions, that direction, could be given as a vector. We don't know what that vector is, but it has been labelled with the letter A. Similarly, there are a set of instructions that would get you from O to B. You could start at O, follow the instructions, and you would end up at the finishing point B. And that particular set of instructions has been turned into a vector. We don't know what that vector is either, but it has been given the label of B. At no point in this question are we ever going to find out what A and B stand for in terms of vectors. We're never going to apply any numbers to them. And that's why this is one of those algebra type questions where we're just working with the letters all the way through. But because they are standing for vectors, and we know they stand for vectors because I've told you, and because they're in bold, we know they stand for vectors, they still behave like vectors do. So we need a couple of other bits of notation as well. A couple of other technical points. First thing to notice, the arrow on the vector and the arrow on the diagram are important. A is the direction from O to A. If we wanted to go the opposite way, we'd have to travel backwards. So instead of going up, we'd go down. Instead of going left, we'd go right, but we'd have to travel the same number of steps. The number would be the same, but in the opposite direction. And if it's in the opposite direction, the sign will be different. We'll have the opposite sign. So for example, if we wanted from A to O, the other way round, that would be given as the vector minus A, because it would be backwards. The signs will be opposite. We'll be moving in the opposite direction. Left instead of right, right instead of left, up instead of down, down instead of up. And if we wanted B to O, we wanted to start at B and move to O, then we would be moving along the vector minus B, because we're going in the opposite direction. We're going against the flow of the arrow. Next thing to notice. Let's have a look at the direction from D to O. If we started at D and moved to O, that could be given by a particular vector. There would be a certain set of steps that we could follow. But there is something interesting about the direction from D to O. Compare D to O to B. This length here and this length here are the same. They are exactly the same length. They are also parallel. They are one line, which means they must be parallel. Same direction, never moving any closer or further apart. They are one line, so they must be parallel. If they are parallel and the same length, then the directions, the way to move from D to O and the way to move from O to B must be the same. They're the same length and they're parallel, same length, same direction. They must have the same vector. The start point is different, the end point is different, but the way of moving between them is exactly the same. So that means that D to O must also be B. Different start point, different end point, but parallel and same length. So they must have the same directions, the same way of getting from one to the other, from start point to end point, which means they have the same vector, which means they have the same letter. We can also apply that from C to O. C to O and O to A are parallel and the same length, so the vector, the direction from C to O and O to A must be the same, which means this one here in the same direction must also be A. Why is that useful? Well, because we can start to put these things together to answer questions like this. Question 1. Find in terms of A and B the vector A to B. So we want to move from A to B. We know nothing about the information getting from A to B. But when you go from one place to another, you don't necessarily have to go directly as the crow flies. You can go in any direction you want as long as your start point and your end point are where they're supposed to be. The direction you take does not matter. So what if, rather than go directly from A to B, why don't we go A to O and then O to B? We'd still get there, we'd still get where we needed to, and we have information about that. Let's go A to O, first of all, and then let's go O to B. Well, A to O is moving against the flow of this arrow. And we've already said that A to O is given by the vector minus A. If A is from O to A, whatever that direction A stands for, we're going the reverse direction, so we're going minus A. And now if we want to go from O to B, well, that's simple. That's just given as that direction B, whatever that happens to stand for, B. So if we put them together, we're going to do one, then the other. This idea of doing one set of instructions, then another, is us adding these vectors. So A to B will simply be given by minus A plus B. Minus A plus B. Question 2, very similar kind of thing. We want to get from A to D, find in terms of A and B, the vector AD. Again, arrow over the top, A to D. So we know nothing about the way to get directly from A to D, but when we travel between two places, we don't necessarily have to go as the crow flies. We can go any direction we like. So we could, for example, go A to O, and then O to D. A to O, and then O to D. Well, A to O is given by minus A, and O to D is given by minus B, because we'd be heading backwards along the arrow. So overall, if we were moving A to D, then we'd be going minus A, minus B. Vector algebra. Setting up a direction as a vector and then coding for it with a letter. If it's in bold, it's a vector. It's a particular direction. If we're going against the flow of the arrow, we are reversing it. We've got a minus vector. And any lines on the diagram that are the same length and are parallel will have the same vector. They will have the same direction information to describe them.